Hi, APChem. Welcome back to acid and base applications. So we are on the last topic that we really need to talk about when it comes to the application of acids and bases, when it comes to equilibrium, those two things together. So after this, what we're going to do is move into a similar idea of the application of equilibrium as it pertains to precipitation. So that's the next topic that we're going to do. But as for now, all we really have to talk about are acid and base indicators. So you already know a little bit about acid-base indicators. You know we use it in a titration. You know that the indicator is a weak acid. You know that the indicator has two different forms that are both different colors, and that the point at which it turns colors is called the end point. So, again, we talked about this difference of equivalence point versus end point. It's a small detail, and it usually doesn't matter unless you are designing your own experiment. And then it matters greatly. You need to know that the equivalence point is where the concentration of your acid is equal to the concentration of your base. That's where the equivalence point happens. The end point is a color change. And we're going to talk a little bit more about what that actually means for the end point today. But just so that you know, not all indicators change color at the same pH. In the same way, not all combinations of weak acids and weak bases hit their equivalence point at the pH. So it's kind of a complicated machine that you have to design when you're designing your titration experiment, right? You have to know what the pH is when your concentration of acid is equal to your concentration of base, right? That's going to depend on the ions or the salts. Which ions are present? What's the conjugate of your base? What's the conjugate of your acid? And those two ions are going to determine the pH when the acid is equal to the base. The end point pH is determined by the Ka of your indicator. So like we talked about before, your indicator actually is just a weak acid. It is a hydrogen ion connected to an anion. And when that hydrogen is on, the indicator is one color. When that hydrogen is off, the indicator is a different color. So indicators are really specialized, very cool molecules because not all acids and bases turn color when they have a hydrogen attached versus detached. And actually, if the acid itself did change color when the hydrogen was attached versus detached, it could be its own indicator. And we actually see this with potassium permanganate, for example. That's the substance that we used in our kinetics lab, right? It was the purple one. So when you are in a MnO4 minus form, right, it started as K, MnO4 minus, and then we titrated that, and the reaction occurred so that the molecule would react, and one of the products was Mn2 plus ion. And when it's in the permanganate form, it's the purple. When it's in the manganate form, it's colorless. So something like that can actually be its own indicator because it actually changes color, but most molecules don't change color. In fact, all the really common strong acids, strong bases don't change color between their acid conjugate base form. The common weak acids, weak bases also don't change color. And so we need to put in a molecule that is colored so that we can see where this endpoint occurs. Now, indicators are going to be really weak acids because we don't want them to be stronger than the thing we are titrating, right? If the indicator was a stronger acid than the substance we were working with, then the indicator would react instead of the substance we were working with. So it really does have to be a very weak acid so that it doesn't get in the way of the reaction we're studying. So we are going to write the indicator as if it's a weak acid. Remember, our general format of a weak acid is HA, a hydrogen with an anion. Now, to indicate that it's not the weak acid that we're studying, that it's a different weak acid, so weak that it doesn't interrupt our reaction, we're actually going to replace the A with an IN. So IN for indicator, right? So our anion in this case is going to be represented by IN or IN minus, right? And then we're still going to have that H attached. So when I write a general format for an indicator, it's going to look like this, HIN. Now, usually we don't write the actual molecule for the indicator because most indicators are giant molecules. And so it would take us a very long time to actually write out all the atoms involved. So we don't. We just write IN for the anion instead of the actual anion. So what would the reaction be? This would be a good time to pause and see if you can write a reaction with this indicator. Pause here and see if you can do that. So the indicator is going to react just like a weak acid. We can write it as if it's reacting with water, H3O plus IN minus. And remember, we ignore water because it's a liquid and it doesn't affect the K. Or we can write HIN just as if it just dissociates into H plus and IN minus. Either way we write it, we can write a K. We're going to get the Ka from it. And so the Ka would be equal to the products over the reactants. And that's going to be your Ka equation. So again, this Ka, remember, is a ratio of your products over your reactants. So when we talk about where this color change occurs and the fact that the color change is dependent on the Ka, what we're really talking about is the ratio of your colored molecules. This ratio of the anion and the weak acid form. And so where the color change occurs is dependent on this ratio. This ratio is dependent on the Ka, right? Where this reaction actually hits equilibrium. Where does that equilibrium occur? And we can push the equilibrium forward or backward by adding bases. Bases would react with our acid and push it forward, or we can add an acid. Acid would react with the conjugate base here, the IN minus, and push the reaction forward. So we can push this equilibrium forward or backward by adding bases or acids. The other question is, where can our eyes actually perceive a different color? And some work has been done with this. And what scientists have decided is that eyes can actually perceive a color change when it's about a 1 to 10 ratio. of HIN to IN minus. So if you start with HIN, right? If you have like, let's say 5 molar HIN and you have none of this stuff initially, you actually have to build up this change. Actually, you have to react the change on one side, right? We're going to lose our HIN molecule. And we have to build up the change on the other side before you can actually see a color change. It's not going to happen. You're not going to be able to perceive a color change the minute you get some IN molecules present. You actually have to kind of build them up. And when it's about a 1-to-10 ratio between the two things, the acid and the conjugate base, then our eyes can perceive that it's a different color, and that's what we would call the endpoint. Okay, so it's dependent, the endpoint is dependent on this ratio of the weak acid indicator and its conjugate base, and we're going to be able to perceive the endpoint when the ratio is about a 1-to-10 ratio. So interesting to know. Not necessarily a crucial piece of information, although Zoomdal is going to make you work with that information a little bit, try and apply it, bring your knowledge and your context and your skills all together to try and apply it. Okay, so for example, we have bromothymol blue. It's an indicator with a Ka value of 10 times 10 to the negative 7th. So you can see from the Ka value, it's a pretty weak acid. Right? It's about on par with water. It's about as weak as water. So most of these indicators are going to toe that line in between the weak acids and the useless acids, just like water does. It's yellow in its acidic form. It's blue in its deprotonated form. Okay, so if we put a few drops of this indicator in a strongly acidic solution, then the solution is titrated with NaOH. At what pH will the indicator change first be visible? Okay, so we're being asked about pH, right? And the pH is for this reaction between HIN and the IN minus form. Notice it's an acid with its own conjugate base. So we here can use the Henderson-Hasselbalch equation. We have the acid and its conjugate base present. We know we can first perceive this at what ratio? At 1-to-10, right? We start with HA, lots, and then we slowly start to build IN plus. And so we're going to have, when we can first perceive the change, we're going to have more of our weak acid form present than we do our conjugate base form present. Okay, so log 1/10. We know the pKa, negative log of 1 times 10 to the negative 7th. And then we can calculate pH. Okay, so if we plug all this in, this is going to be a 7. Log of 0.1 is going to be a negative 1. And so at a pH of 6, we're going to be able to perceive a change. Okay, so good things to know. If you start, all of this is telling us, all of this, the fact that we start in highly acidic solution and then slowly add NaOH means we're going to have more HIN form when we perceive the change. Also knowing it's just a weak acid, right? I know it's kind of new and scary, and the concept is a little bit more, seems a little bit more complicated, but it's just a weak acid. So we can still use all the things we can use with weak acids and their conjugate bases, like the Henderson-Hasselbalch form. Okay. So when you choose an indicator, you have to make sure that it's its endpoint is going to line up with your equivalence point, right? So basically, an indicator is usually fairly useful over plus or minus 1 pH. So that color change is going to happen over a range. Remember, we first perceive it when it's about a 1 to 10 ratio, which means it's going to happen over a range. It's not all going to be instant, right? You don't just have weak acid and then all of a sudden you just have its conjugate base. That's not how equilibrium happens, right? You get this slow shift of like a little bit of weak acid with a little bit of conjugate base, and then more of one, less of the other, more of one, less of the other, more of one, less of the other, right? But you always have this kind of balance happening. It's not just going to shift all of a sudden. And so there's kind of a like color change range over which indicators are useful. Now that's okay, because if you look at a titration graph, right, the indicator usually happens, or the equivalence point usually happens at a specific pH, and that specific pH changes quite dramatically with a very small input of volume, right? Sometimes, depending on the strength of your acid and base, sometimes that pH change can happen. It's a pH change of like 9 or 10, and it can happen over a volume change of like a drop. So that's why titrations are kind of a tricky lab technique, because you really have to be precise on the volume that you're entering. But it's also good for indicators, because if the indicator changes at this, difference of a pH of 1, you're going to hit it with a tiny amount of volume added. You're going to cross over that pH range of the indicator and then some. So it's okay that it's a range. You just have to know it's about a range of plus or minus 1. Okay. So you want to choose an endpoint that's close to the equivalence point. And so this is kind of our thought process in choosing an indicator. Okay, so for example, if we have a 0.1 molar HCl, 0.1 molar NaOH titration happening, right? So our equivalence point is going to be when HCl is equal to NaOH. That means the only ions present are going to be Cl minus and Na plus. Well, neither one of them are a significant acid or base. And so our pH is going to depend, therefore, on the autoionization of water, which means at the equivalence point, our pH is going to be 7. This doesn't always happen. Remember, it only happens because of what is present when our acid is equal to our base. If either of these ions was a weak acid or a weak base, then that pH would not be 7 anymore. All right, initially the indicator starts in acidic solution, so we're going to be in the HIN form. The color change color change occurs when we build up enough of that conjugate base, so it's going to be a ratio of 1 to 10. And so what pH do we want our endpoint to occur at? Well, we take this and we plug it into the Henderson-Hasselbalch equation. pKa of our indicator plus log of 1 over 10. So we already saw this was going to be a -1. So if we want a pH of 7, then our pKa has to be around 8. So we want to choose an indicator that has a pKa around 8. And then we can we can just drop our indicator in and forget all about our indicator until it changes color. So that is kind of the process you would go through when you're choosing an indicator. Now, do we have to choose one that has the color change that occurs exactly at the pH? This is what we were just talking about, and the answer is no. Notice for like phenolphthalein, which is the pink to clear. This is the really famous indicator that a lot of people have worked with. If you do a titration, you'll probably do one with phenolphthalein. Phenolphthalein has an endpoint that occurs around a pH of 9, right? And we just saw that the end point for HCl NaOH is going to happen around 7, right? So can we use phenolphthalein with that one? Well, yeah, actually we can, because look at this pH change that occurs. Our pH is going to change from about 3 to over 10. So let's say like 10.5. Okay, so we get a pH change of like 7.5 with almost no change in volume. I mean, if you go to barely to the side of one, barely to the side of the other, look at that volume change is going to be a drop. So we get this huge, enormous pH change because we're going from all HCl down here to all NaOH up here. There's no buffer there. There's nothing weak present ever. And so, yeah, phenolphthalein will work, even though the pKa of phenolphthalein doesn't exactly match the equivalence point. Now, same thing with like methyl red. If we look at methyl red down here, methyl red has this change that happens, this color change that happens just above 5. We'll say 5.5 at a pH of 5.5. So you could use methyl red for an indicator. You could use phenolphthalein for an indicator. Now let's look at the second curve on here. Notice the curve we were just talking about was HCl to NaOH, right? Well, we have a second curve on here that is a weak acid being titrated with NaOH. So we start down here with all weak acid present. In here, we have our weak acid and conjugate base present. Our equivalence point is going to happen a little bit higher because we have the conjugate base present at the equivalence point. When HA concentrations are equal to NaOH concentrations, we have none of either of this left. We just have the ions, which would be A minus from our weak acid and then Na plus from our strong base. So Na plus isn't going to affect the pH anymore, but A minus will. So our equivalence point is a little bit higher. And notice that the volume change, let me erase this so you can see that volume change more clearly. Notice that our volume change, our pH doesn't change quite as drastically, and that volume change for that pH, right, is going to be probably a drop, but it results in a smaller pH change. So would methyl red be a good indicator in this case? No, it wouldn't. Phenolphthalein would still work, though. Even though our equivalence point is at the very bottom range of phenolphthalein, that color change still is completed by the time you get out to the point where you just have NaOH building up again. So does the endpoint have to be exactly the equivalence point? No, it doesn't have to be exactly the equivalence point. But the weaker the acid you get, the more precise your endpoint has to be, right? For something that's strong acid, strong base, where we have a huge pH range that occurs, a huge pH jump that occurs within that drop from just having HCl present to just having NaOH present, you can be a little bit more careless with your indicator choice. When we get a weak acid, however, we get a much smaller pH jump that happens because we're going from a buffer present, HA, A minus, to NaOH present. It's going to be a smaller jump in pH. You have to be a little bit more precise with your indicator choice. Okay, finally we get to looking at a couple common indicators. So this chart shows you the color change that occurs for a bunch of different indicators. Remember that color change, that pH of the color change is dependent on the Ka of the acid. And then we're also going to, if we're going from acid to base, it's going to start about at this log of 1/10, at this ratio of about 1 part A minus over 10 parts HA. And so you can see the color change starts at that 1:10 ratio for all of these, right? But they all have different pKa's, so that color change happens over different pHs for all of them, and that's why you actually have to go through the process of figuring out what your pH of your equivalence point is going to be, so you can match it with the correct indicator. That's going to actually change color over that range. You can see it ends when you're about at a ratio of 10 A minus to 1 HA compound. And most of this, from the start of the color change to the end of the color change, it's about a range of like 1 to 2 pHs. It covers a pH range of about 1 to 2. And you can see some of the really common ones. Here's phenolphthalein. It's colorless to pink, and that's going to happen about a pH of 9. So it's a really common indicator to choose for a strong acid, strong base titration. Phenolphtalene's cheap. Phenolphthalene's really safe. You can actually drink phenolphthalein. It's a diuretic. It will cause you to have diarrhea, but it won't do much else than dehydrate you. So it's really safe. It's really cheap. It has a really convenient pH. It gets used a lot. Bromothymol blue is another really common one. It goes yellow to blue, and it's over a pH range that's pretty good for like a weak acid, weak base titration. And then depending on, methyl red is another really common one that can indicate for kind of some different weak acids or weak bases. And then depending on what industry you're in, what you're trying to do, what acids and bases you're dealing with, you might choose some of these other ones. So there's your overview on indicators. And from here, we move on to looking at equilibrium in terms of precipitation. So let me know what questions you have. I will see you in class.